Hello, and welcome to our presentation on the Quick Release Tool OTRA Mk II, or Omnidirectional Tool Retention Apparatus Mk II, presented by the Blazars, Andrew Davison, Miguel De Leon, Colton Mateka, and Trevor Smith. Today's presentation contents are split into three major sections. Section 1, Project Goals, Criteria, and Constraints. Section 2, Modeling and Analysis. And Section 3, Testing Operations Plan, followed by a Q&A session. And with that, I'll hand it over to Miguel De Leon to present Section 1.
Thank you, Andrew. Now for Section 1, Project Goals, Criteria, and Constraints. For our project goals, we are to design a two-piece quick release mechanism, test out the 3D printed prototype for its functionality, finalize the specs, manufacture the real prototype, test the prototype, and do the showcase at TSGC. Now for our criteria and constraints. We are to have a 1x1 4-hole square bolt hole pattern. It should be capable of holding 15 pounds of weight in Earth's gravity. It should require minimal force to detach the tool from the utility belt. All parts should weigh less than 2 pounds, and it should fit within a volume 4x4x3, and lunar dust should not impede the functionality of the system. The device should be easy to use. It should be operable outside the line of sight and by one hand. It should be operable with a large and bulky spacesuit glove. It should not have sharp edges or holes. The materials that we can use are aluminum 6061, aluminum 775, any series of stainless steel, and Teflon. Here for our materials and applicable standards, we have the standards for aluminum 661. We have NASA's system integration for operator reference when using the system. We have NASA's heat treatment for steel alloys. We have NASA's human integration design handbook. We have OSHA's occupational safety and health hazard standards. And here's our quality function deployment. Here, as you can see, we have our requirements, and we have our engineering metrics that satisfied it. We have our cost, weight of the device, volume of the device, force needed to detach the device, the 4-hole bolt pattern diameter, and the yield strength of the material. And now for our section 2, modeling and analysis, Andrew Davison.
So for modeling and analysis, we'll go ahead and start off with the isometric and orthographic views of the OTRA Mk II, starting with the belt piece. The thickness, including the track width, is just over 5/16 of an inch, and the width and height are equal at 1.845 inches. Moving on to the tool piece, we can see that the thickness is 3/4 of an inch and that the width and height are equal to that of the belt piece at 1.845 inches. Seen here is a striking comparison between the OTRA Mk I and OTRA Mk II, emphasizing the vast size difference between the two. During a redesign, it was discovered that a large amount of space could be saved simply by moving the plunger from the belt piece to the tool piece. This significant design improvement allowed the OTRA Mk II to be 6.5 times lighter and take up less than a fifth of the space occupied by the OTRA Mk I. The functionality of the OTRA Mk II is simple. A female track on the belt piece guides a male disc piece into position such that a ball spring plunger can engage a detent and lock the given tool in place. In addition to the previously mentioned repositioning of the plunger, the OTRA Mk II now incorporates a guide throat for imperfect alignment of the tool and belt piece, which should make storing the tool easier out of line of sight. As for pre-built components, a ball spring plunger was chosen as the retention mechanism, with the requirements that it have fine tolerances, have a suitable side force, and be easily replaceable. As with the OTRA Mk I, the Mk II's plunger is a friction-bearing type, as it possesses extremely fine tolerances that would prevent dust ingress into the spring chamber. Note that the new plunger now utilizes a slotted head, as opposed to the old plunger's hex head. The side force is the force that needs to be applied to remove the plunger from its detent, and ultimately is the force the astronaut would have to apply to remove tools from the utility belt. It's calculated with the simple equation that you see here, where the side force is equal to the spring in force divided by the tangent of the countersink angle theta divided by 2. In our case, the countersink angle was 73 degrees and the spring in force, which was calculated using the spring constant and maximum spring deflection expected during operation, was 4.70 pounds. This resulted in a side force of about 6.35 pounds, which should be easy enough for the user to remove tools, but not so easy that they fall out unintentionally. And with that, I'll hand it over to Colton Mateka to explain our FEA results.
Thank you, Andrew. This slide shows the setup which we use to perform finite element analysis in SOLIDWORKS simulation. Not knowing exactly what tools would be used by the astronauts, we could not replicate a tool for the simulation. Therefore, we simulated the tool instead using an approximately 2-inch cube. The 15-pound distributed load could then be applied to the cube and transferred to the tool piece via the required countersunk screws. Additionally, the back of the belt piece was fixed in place to a flat geometry in order to simulate an interface with the utility belt. With the belt and tool pieces interfaced, performance of the OTRA Mk II could be analyzed. This figure shows the stress results or the stress plot developed from the simulation. Identified in red is the location of the max stress, which was determined to be 3.366 kpsi and occurred on the collar of the toolpiece. Considering 6061 aluminum has a yield strength of 7.999 kpsi, the safety factor for the prototype was determined to be approximately 2.4. This satisfied our original goal of hitting a safety factor of 2. It is worth noting that we anticipated max stress for the prototype would occur on the belt piece along the slide. Although max stress for the belt piece did occur on the slides, the maximum stress occurred at the base of the slides. Additionally, the magnitude of the stress was only 1.526 kpsi, significantly less than the overall maximum stress presented on the previous slide. We do anticipate that a wider tool would generate a greater resultant torque, thus increasing the stress and strain along the slides and potentially causing the pieces to separate. However, as previously mentioned, it was never disclosed exactly what tools would be used by the astronaut. Considering the product requirements alone, this analysis did validate that the OTRA would not only meet, but also exceed the loading capabilities. I'll hand it over to Trevor Smith now to discuss the details corresponding to testing of the prototype.
Testing the OTRA was split into 3 sections. First, testing functionality in the presence of simulants. Second, its load supporting capabilities and required removal force. And third, its functionality and retention while performing simulated work. For the first test, we purchased 2 simulants, Martian and Lunar, from the Exolith Lab of the University of Central Florida. These simulants are trusted and purchased by NASA and reflect over 80% of the soil composition for each respective surface. Our main concern was simulant impeding the friction-bearing plunger, having a tolerance of about 25 microns. Specifications and particle analysis performed by the Exolith Lab show only 30% of the simulant particles could possibly intrude the plunger device. Testing consisted of 2 assembled OTRA prototypes placed in simulant, 1 in Martian and 1 Lunar, then shaking the bag completely submerging them. Then they were removed and cycled 10 times, being weighed before and after each test to quantify dust intrusion. In testing, the dust collected in surface gaps, slightly increasing removal force, but returned to its original state after being cycled and knocking off the dust. After cleaning the surface with compressed air, the device has only incurred an added weight of 2 to 4 10,000ths of a gram per each test. Next, a load test was conducted using the apparatus on the left, securing each component to their own wood block via wood screws. The female piece on the block clamped to the table had the throat of the device oriented up. Where the OTRA interfaced, lab weights were added to an eye hook in the image to the right. Removal force was tested similarly, but with the female piece oriented down so the male piece could fall freely. The binding, caused by a moment arm shown to the left, interfered with the OTRA's removal test. The image on the right shows the addition of fishing line needed to apply tension, keeping the blocks level and removing the binding. Consequently, this binding requires the separation of the OTRA to be deliberate. The results of the testing shown largely agreed with our expectations, except not being able to test for the yield point, being limited in quantity of lab weights at our disposal. Nonetheless, the OTRA met or exceeded our requirements in these tests, verifying support of 30 pounds and a removal force of 6.21 pounds. To test the OTRA's ease of use and ability to retain tools, a maneuver test was performed. During this test, a Blazar simulated natural movements on an EVA mission by walking, kneeling, bending, and tool use, using large gloves. While removing and replacing tools to the OTRA. The OTRA proved effective and easy to use outside line of sight, requiring minimal force to remove and return to the utility belt. To prove the OTRA does not require a retention device, we performed some ridiculous and extreme movements, all in Earth's gravity. While the cartwheel wasn't great, the OTRA's ability to retain tools was. On behalf of the Blazars, I would like to thank everyone for their attention and open the floor for questions.